Good afternoon. Welcome to today's SCA webinar with Dr. Jim Smolin on monitored well flow evaluation production logging. Before we start today's webinar, we'd like to ask a few questions of the audience so we can learn a little bit about the demographics of those who are attending. So our first question is, what is your primary discipline? We're starting to get some votes in now. Looks like we have quite a few geoscientists in the crowd, but also a fair number of petroleum engineers and petrophysicists. Still getting responses. Most of you have voted now. It looks like we have 40% geoscience and 30% petroleum engineering. So let me share that information. And then we'll go to our next poll. The next poll is, how many years of full-time experience do you have in the upstream oil and gas industry? So we're starting to get the responses now. Quite a few of you have over 30 years, but there's also a good number of you in the 1 to 10 year range. So it looks like those are the two largest categories. Almost all of you have voted. So I'll go ahead and close the polling and share those results. So you can see more than half have over 30 years, with the next largest group in the 1 to 10 year range. So as we start today's webinar, I'd like to remind you that you will be muted during the presentation. We'll have question and answer at the end of the presentation, and you will be anonymous. So go ahead and start typing in your questions throughout the presentation, and we will get to as many as we can at the end of the presentation. And I'd like to introduce Dr. Jim Smolin, who's our featured presenter today. He's going to be covering the topic modern well flow evaluation, production logging. Dr. Smolin has over 30 years experience in cased hole well logging. He started his career with Schlumberger, and in 1980 became the director of petroleum computing and has numerous publications to his credit. He has degrees from Northwestern and UC Berkeley. Dr. Smolin also teaches a class on cased hole log and production log evaluation that's being offered in Houston, Texas in June. So if you're interested in attending that class, you can contact us to either come to one of the public classes, the one in June, or to schedule it in-house. I want to remind you that we've been offering these webinars as a series to feature our instructors, and we have two that are coming up on the calendar next week. Amy Fox on geomechanics, and Bob Shoup will be joining us in May talking about dry hole avoidance. So SCA is a source for consulting, direct hire, projects and studies, and training. So be sure and contact us if we can help you with any of these areas. And so at this point, I'd like to give the presentation rights to Jim Smolin. And Jim, it's all yours.
Okay, how do I advance it? Okay, we're going to start out discussing some aspects of cased hole and production log evaluation. Cased hole logging is really a fairly broad category, and if you look at the various aspects of cased hole logging, excuse me, various aspects of cased hole logging, you'll find that there are a number of broad brush categories that we can look at. The first, and one that many of you may be familiar with, are the so-called formation evaluation techniques, where you can actually evaluate the water saturations, oil, gas content in formations using a pulse neutron tool. So we can evaluate formation liquids, formation fluids through the casing using such pulse neutron tools, excuse me, like the Sigma tool, or alternatively the carbon oxygen type logs. There are also through casing resistivity logs, sample taking techniques that will drill a hole through the casing, and which could be repaired, and other services that are not very common. The second fairly broad brush category that we're going to be looking at, or we're not going to be looking at, but is a part of the cased hole arsenal, is the so-called well-bore well integrity logs. Well-bore means we're looking at the very basic tools to measure the quality of the cement job. You know, that cement is pumped down through the casing, comes back up, and hopefully fills the annulus. Now, we can measure the quality of the cement, that is the quality of that cement fill, by use of a cement bond log or logs. Typically, a CBL would have a 3-foot or 5-foot receiver spacing, and from that we would develop some amplitude measurement, which gives us an idea of how the cement is contacting the casing, and also you know, whether or not we have a full or 100% annular fill of cement. We will also in the course look at various pulse echo tools, those with rotating heads like the Schlumberger ultrasonic imager, or alternatively the Halliburton circumferential acoustic scanning tool. Well integrity is a little more than merely the cement quality, though. Oftentimes when you look at the production profile in a well, sometimes things are happening in places that you don't expect. Well, we also have well integrity services. These include the various mechanical services, multi-fingered calipers and like that, and also a number of electromagnetic tools to evaluate the quality of the casing, the wall thickness, and so forth. What we're going to focus on today, though, is the downhole fluid movement. This is the third of these three broad brush categories. Downhole fluid movement it basically is a wireline technique whereby we run a tool typically called a PLT, production logging tool, and this tool has a spinner flow meter on the end of the tool. It has a fluid identification device on the tool, and the intention is basically to measure the flows downhole, what their values are, what phases are present, water, oil, or gas, and where they are coming from. The most common application, of course, is, hey, where's the water coming from? And we will run a PLT package typically to distinguish which zones are producing water, and hopefully we can make some kind of remedial action. There's another broad brush category which we do not generally cover, and that's this other are mechanical services, free point or stuck point indicators, that sort of stuff. We don't get into that. So these three broad brush categories are those categories that are discussed in the cased hole and production logging course. This downhole fluid movement is where we're going to be today. Okay, first of all, when we run a PLT, we're looking for fluid entries downhole, and that means we're looking for the flow rates. But the process of making these evaluations is typically a two-step process. First of all, remember the PLT has a spinner flow meter on that tool. With that spinner flow meter, we evaluate the bulk flow rate of the flow. This shows some of the spinner tools. Here we have on the left the so-called small diameter tool. What that means is that the spinner is basically contained within the tool housing, and it's a small diameter. Typically, the standard size for most tools is 1 11/16 inches in diameter. If you use this tool, I have to forewarn you, it absolutely positively has to be centralized. Doesn't have to be precisely centralized, but if you don't centralize it, it had been reported by studies by Marathon that you get totally erroneous results at 2 degrees deviation or larger. This tool here is the so-called full bore spinner. This tool is basically the workhorse of the industry. What it has is when running in the hole, a collapsed assembly. When you get below tubing, whoop, that assembly opens up into this so-called full bore configuration that you have here. Notice the spinner was folded up. When it opens up, it covers perhaps 50% or more of the cross-sectional area, and that's important. It's important as a general rule to get the largest spinner that you can possibly get in that well. A smaller spinner will be more susceptible to problems that you have with the small diameter spinner. So this is basically the workhorse, and this is what we're going to discuss. There's also another tool that you might be aware of, and that is the so-called basket or diverter type tool. This basket or diverter essentially has a motor-driven centralizer, and you would essentially stop and make a measurement. That motor-driven centralizer sets up an upside-down funnel-shaped structure like we have shown here. The flow comes up, goes through that structure, and is diverted into this center section over here where there is a small spinner. These tools are best used in cases where the flow volume is less than perhaps 1,000 barrels a day, and also the flow is typically multi-phase and deviated. In any case, this is our main emphasis right here, the full bore spinner and its association with a so-called PLT, production logging tool string. This shows what we see when we run a spinner, a full bore spinner, for example. What I have here is I have a well sketch. You'll notice that there is a set of perforations across the interval that I'm highlighting here. There's another set of perforations above that and another set of perforations above that. When the fluid comes in, obviously the fluid propagates up so that the volumetric flow rate here, if there's any, is going to be less in general than what you have above the entry point. Next entry point again will give us a volumetric flow rate, which again is higher. In any case, if you look at a log, this is what it looks like. What we're looking at here is a spinner flow meter series of logs. There are 5 runs shown here at different constant velocities, 45, 64, 79, 117, and 164 feet per minute. Now, what you're recording here as we're logging down at a constant speed, you'll notice that down here where the flow is 0, you're going to have the slowest logging or the slowest revolution per second, or the fewest. You get above this first entry point and the flow is now propagating up. The tool is logging down. So we have an increase of the RPS at points where there is an entry to the fluid. We have an entry here, as you can see, between intervals B and C. We have another entry over here between intervals C and D, an entry right up over here. So you can, as a general rule, see that what we have are series of relatively constant flow rate. And these intervals, here we have a steady flow rate, here we have a steady flow rate, here we have a steady flow rate, here we have a steady flow rate. Those steady flow rates are the intervals at which we would do our analysis because we can be confident in what we're looking at. The other thing to notice from a quality control standpoint is each one of these is at a constant logging speed. The only difference between any of these logs is going to be the logging speed. So the space between the logs, if the logging speeds are constant in each of them, the space between the two should stay exactly the same. So as a quality control, when you look at a series of runs, they should all look alike, but simply be displaced from each other as a result of the different logging speeds. Okay, this is what the logs look like. This shows how the logs would be incorporated and how the interpretation process would be done to get here. Notice what we have again. We have 1, 2, 3 stable intervals. We have a set of perforations here and another set of perforations here. So we have an entry and an entry. If we log down again, you see that here is a down run. It's at a constant speed, so we have a fairly high rotational speed here because the log is moving down against the fluid. These are, by the way, down runs. So here we have a run log down. Here we have an entry. Whoops, excuse me. Here we have an entry. Here we have an entry. And we have basically 3 logs here. Quality control, they're all evenly spaced. Excuse me. They're all reasonably spaced relative to each other. Here we have up runs, same situation. We're recording 2 things, logging speed and rotational speed of the spinner. What do we do with this data? We take that data and we create a so-called cross plot. This is a cross plot where we're plotting cable speed versus rotational speed of the spinner. So if we were to look down here at the lowest interval where we hope the flow is 0, what we would get is 140 feet per minute. This is the cable speed. And on a scale of 0 to 10 RPS, we would be reading approximately 7 RPS. So I come over here, 140 feet per minute, 7 RPS, and that gives me point F. I do the same for point E, 100 feet per minute, 5-ish RPS, 50 feet per minute, 2 RPS, and so on. So this creates the up and the down run cross plot data. This is our static response. When we encounter a flow, remember the whole business shifts equally. So what happens is when we replot this data for this interval, interval B, what we have is 1, 2, 3, 1, 2, 3. We have this set of curves right here and here. And what you're looking at down here, this curve with just 2 thin lines, that's our original 0 response. So the effect of the flow is simply to take this 0 response and shift it in this direction, an amount equal to the flow. Shift it in this direction, an amount equal to the flow. So this gives us a means of calculating the flow velocity. What happens when we get the velocity? Well, then we have to convert it into the bulk flow rate, barrels per day, or whatever units you want to use. This illustrates one of the problems that we have. If we take that RPS and multiply it times the cross-sectional area of the pipe, in general, we're going to find we get too high of a velocity. That being the case, we have to cut it down a little bit. Why do we get too high of a velocity? Well, if you look at this figure, you'll notice there's a flow profile. This is a laminar profile. In this case, the flow is very rarely laminar. It's almost always turbulent. And what that means is the flow profile will look fairly close to the wall here and then be fairly flat across this upper interval and come back close to the wall again. Anyway, the point is the flow meter analyzes or measures only that fluid which is contained within the envelope through which that spinner passes. And as a result, the spinner will detect the velocity in interval I. The true average velocity is going to be typically somewhat reduced from that. Most softwares will have a number, will calculate that. Alternatively, if you're doing it by hand, we would typically use a correction factor of about 0.83, which is typically within 2 or 3% of reality most of the time. This is how the data might be presented. What I have are 2 different type presentations here. This one here shows the cumulative production coming from bottom up. So in interval A, for example, we might have 0 flow. In interval B, we may have 200 barrels a day. So we have an entry here of 200 barrels a day. You can see the entry profile on this figure over here. Come back here, we're moving up. We go from 200 barrels a day to 500 barrels a day or 600 barrels a day. Well, that means this entry is 400 barrels a day. And that entry is shown here on the entry profile. We go from 600 barrels a day to perhaps 900 barrels a day. We have an entry of 300 barrels a day. This is the as shown here on the entry profile. So this is a cumulative production rate as we come up whole. By taking the differences between the cumulative production rates across the entry points, we can get the individual entry values. Okay, this now again is our bulk flow profile. Remember, we're not home free yet. If we're looking for where the water's coming from, hey, we still don't know. So let's take a look at how we make measurements of what the fluids are downhole. The first technique that we have, and one that's been around for a long time, even longer than I've been with the industry, is a gradiometer. A gradiometer measures a pressure differential, dP/dZ, over about a 2 foot 70 centimeter interval. Now, that dP/dZ can basically be calibrated. In fresh water, it would read 1 gram per cc. In air, it would read 0 grams per cc. So clearly, if you were in fresh water, you would be reading dP/dZ, which would be 0.433 psi per foot for your information, but it would be calibrated to read 1 gram per cc. How do we use this tool? Well, suppose we have a mixture of 50% water and 50% air, and it was well mixed and churned up. What would we see in terms of the bulk density? Well, we would see a bulk density contributed 50% from the water, 1 gram per cc, and 50% contribution from air, 0 grams per cc. So we would have an answer or a bulk measurement of 0.5 grams per cc. That would indicate 50% water, 50% gas, or air rather. Another tool that we have to measure the nuclear fluid density, and there are very many different configurations of this tool, is a nuclear fluid density device. Essentially, it has a provision to collimate a gamma ray beam over a 4-inch to 10 centimeter interval. The flow will, as a general rule, come up and go through this interval. These here are basically the cage of an open tool. So the flow comes up and goes through this interval. Hopefully what you have in this 4-inch section is representative of the fluid that you have out in the wellbore. That being the case, again, you make a measurement of the bulk density. Again, there are a lot of different configurations for this kind of a tool, some of which at first glance you wouldn't recognize. Nuclear fluid density, and there are some non-nuclear density devices, vibrating reeds, and so on. Basically, if we have two phases in the wellbore, that is oil and water, we have one fluid identification device required. For example, that dP/dZ measurement, that would measure a bulk density from which you can determine how much gas, how much water you have. No problem. But if we have a third phase present, and there's an appreciable amount of it, then all of a sudden we need a second fluid identification device. This illustrates a device called a capacitance or a dielectric tool. Again, these tools will have widely varied configurations, but this particular one has a core, This has a core, you see here a core, and an outer jacket, okay? The flow would come up from below and ram into these holes and hopefully fill this annulus with a representative sample of fluids that are outside the tool. That being the case, the core and the outer jacket become the plates of an annular capacitor. So we measure the bulk capacitance of this fluid within this annular capacitor, and then that bulk capacitance again gives us a means of ascertaining how much water, how much oil. Well, actually, it mainly discriminates the amount of water and is a fairly poor discriminator between oil and gas. But basically, it discriminates how much water you have present. So these are some of the devices. More recently, we've seen the development of some tools which started out at the onset to be directed towards some more horizontal situations. One tool that came digital entry fluid imaging tool. I don't know what happened to the I. I guess it sounds like a deficit, so they don't like to use it. They call it simply a depth or flow view. In any case, this tool is an array of, it's a 4-arm centralizer on which you have an array of 1, 2, 3, 4 resistivity probes. A resistivity probe is capable of discriminating water from hydrocarbon, but as a general rule cannot distinguish oil from gas. The other tool here, which came out about the year 2000, possibly 2001, is called a GHOST, Gas Hold-Up Optical Sensing Tool. This particular tool essentially has 4 sensors on it, just like the DEFT. As a matter of fact, it's the DEFT tool, basically, with different sensors. So what this sensor has is it has optical probes. These optical probes are capable of discriminating gas, but not discriminating liquids like oil and water. Cannot distinguish liquid from water, but can distinguish gas from liquid. So just to give you an idea how these tools work, you have 4 probes. Here is a GHOST probe indicated. The probe is over here. As you're logging, the tool goes through either slugs or bubbles, and what you're going to see basically is this. Hold on. What you're going to see is you're going to detect liquid, gas, liquid, 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 gas, liquid, gas, liquid, liquid, liquid. And what you get is a binary or piano key pattern. You record it for a certain period of time, perhaps 10 seconds, and then you look at it, and obviously the white part, in the way it's set up over here, will be liquid. The black part will correspond to gas. So if you look at the track that you have, what is this? So if you look at the track that you have, the white would correspond to liquid, the black would correspond to gas, and you would just simply take the percentage of black over the total length recorded, and that would give you a measurement of the gas holdup as seen by the GHOST tool, okay? So this is what we do, and we are measuring holdup. Let's understand one thing. There are 2 terms. Cut is a fraction of the fluid movement, fraction of the production rate, if you will, downhole or at the surface, whereas holdup is a fraction of the volume present. So if you could flash freeze the fluid, the gas fraction would be the gas holdup, the oil fraction would be the oil holdup, and the water fraction would be the water holdup. Okay, when we look at a data, when we look at the data now, look what we have. So here we have the single, we have here the cumulative flow rate increasing as we go uphole. We're showing here a water entry right here, approximately 3,000 barrels in this case. We're showing basically 100% oil entry over here, approximately 2,300 or 2,400 barrels. And then up here, we're showing again, essentially oil entry about 1,500 barrels. So this is what the result looks like. This is an example of the result using Plato's software. What we have here is water, gas system, and you see the cumulative production here, water coming in toward the bottom, gas coming in a little bit toward the bottom, and then distributed more broadly up on the top. Now, so far we've talked about vertical wells. Vertical wells are fine, and don't get me wrong, the interpretations don't always come out as simply as I've said. But what happens is when things get really messy is when the well gets deviated a substantial amount, especially once it's over about 45 or so degrees. Things become very difficult. This figure here on the right illustrates what's happening. Imagine that we have 1, 2, 3 sets of perforations, and that we have water coming in, but it's coming in somewhere up here. Now, obviously the water is always going to end up at the bottom. It's going to stay full, right? Now, if you look at the light phase that's coming in, the light phase would be either gas or oil. It comes in and bubbles up along the high side of the pipe. Now, if you look at the flow profile, a very peculiar thing happens. When these bubbles go up along the high side of the pipe, they carry, or they act as a conveyor belt, and they carry or push water up with the oil bubbles. So you have a mixture of oil, you have a mixture of oil and water moving up on the high side of the pipe. Now, if the water is vacating this area, clearly it's going to stay full of water. So the water is going to go up, and it's eventually going to fall back down on the low side. And this is the dilemma that it poses. When you look at the spinner flow meter, what do you see? Well, the spinner only sees what's in the envelope through which it passes. And the spinner is going to see a downflow when, in fact, there is a net upflow. This figure highlights it a little bit more, and it also shows that it could be misleading in some ways. Again, here is the high velocity associated with the oil and water production. Bubbles or slugs are running up along the high side of the pipe. The spinner, again, only sees what's in the envelope through which that spinner is flowing, or through which that spinner passes. That envelope is seeing basically the fallback phenomenon, that is the fallback of the heavy phase, the water. Now the spinner sees a downflow. What if you're in a horizontal environment that's very common to run an oxygen activation water flow? So highly deviated or horizontal flows, you have a oxygen activation water flow. Well, let's look at what happens there. First of all, this is a pulsed neutron source here, and it can be turned on for short periods of time, maybe 3 seconds or 5 seconds or whatever. And what's going to happen is these neutrons will propagate out. They will interact with the neutrons in oxygen, and they will convert. They'll interact with the oxygen, and that oxygen will actually be converted into an unstable nitrogen isotope, having a half-life of about 7 seconds. So what that means is the water which is moving up here will become radioactive for approximately 1 minute. That being the case, what are you going to see? You're going to see activation. You're going to see the water moving up, and then all of a sudden, we're going to see counts at the near detector, counts at the far detector. So you could make a time of flight measurement from the source to the near, or the source to the far, or even the source to the gamma ray detector uphole if it's moving fast enough. What does that mean? Well, it means that you're detecting with the oxygen activation tool an upflow. With the spinner, you're detecting a downflow. So what's the right answer? Well, obviously neither is going to be the right answer. And this is the dilemma we have when we run a conventional PLT. We have this problem, and the small diameter spinner has it much worse than a full bore spinner. A full bore spinner can tolerate some of this because it's sampling a wider portion of the wellbore. Okay, let's take a look next at some of the tools that have come about historically to give us an opportunity to evaluate these crazy flows. First of all, and not shown here, Schlumberger had a tool called the flagship tool system, flagship tool. And it's not shown here because the flagship tool had a fairly special application. It was basically a liquid tool. That is, it would discriminate water from oil, and it required a moderately stratified flow. That is, you wanted to see the flow have separate segregatable air layers in the horizontal section. And the tool worked fairly well in that respect. It didn't work very well if you had gas present, because you would be measuring the water flow, and that water flow would be dramatically affected by the presence of gas, and you get crazy answers. Anyway, Shell got together with Western Atlas at that time, currently the predecessor company to Baker Hughes's General Electric position right now. Anyway, this Polaris system is set up something like this. It had a spinner on the end, a small diameter spinner. Ooh, you don't want a small diameter spinner, do you? Well, wait, I'll show you why we have that. Then they have a thing here called the MCFM, multi-capacitance flow meter. The multi-capacitance flow meter is basically a wing, as we have shown here. when you're running in the hole, that wing is contained within the 1 11/16" tool housing. When you deploy it, it comes out, much as we have shown here. This tool also has what's referred to in this slide as a pulse neutron holdup indicator. Atlas has since gotten rid of that and put in their so-called RPM reservoir performance monitor pulse neutron tool. In any case, let's look at this MCFM because this shows the tack being taken by all of the major companies now. Up at the top here, I have a schematic of that MCFM, multi-capacitance flow meter tool. On that MCFM, we have indicated by dots here, capacitance sensors. These sensors are capable of discriminating all three phases, oil, water, and gas. Oil, water, and gas. Now, first thing to do is look, we have 1, 2, 3, 4, 5, 6, 7, 8 individual points along the wellbore, which are measured. If we come back over here, you see that the well can be broken up into 1, 2, 3, 4, 5, 6, 7, 8 sectors, and each sector having some corresponding sensors within that sector. So this is what we're going to do. We're going to look at this sector by sector. So if we look at the sectors here, look what we have. We have 1, 2, 3, 4. Boop, 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 boop. If we have some kind of a perturbation or bubble in the flow or debris, it's going to come by and go boop, 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 boop. 1, 2, 3, 4. Boop, 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 boop. 1, 2, 3, 4. So that disturbance is going to be correlated amongst these 4 detectors. So 1, 2, 3, 4. Okay, and we're going to make a velocity measurement 1 to 3, a velocity measurement 2 to 4, and then a velocity measurement 1 to 4. So we get 3 velocity measurements from each one of these. We put those velocity arrows to indicate what they are at each of the positions where we have 3 velocity measurements. So here, 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 here. Those are the sensor detector positions. And what we come up with is a velocity profile. Okay. Now you wonder maybe what that spinner was at the front. This is a velocity profile measurement right here. So we have 7 velocity profiles, which give us 7 velocity measurements, which give us a very credible velocity profile across the wellbore. Notice that this velocity profile will actually detect these slugs. Leading edge of the slug will come and it'll go boop, 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 boop. Trailing edge of the slug will eventually come and go boop, 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 boop. That slug will detect the presence of gas until this one over here goes by. It'll detect gas here, but obviously it will not be detected over here. Oh, wait a second. So anyway, before I leave this, you can see that we have a velocity for each of these 8 sectors. Oh, never mind. Oh, what did I just do here? Okay, so if we want to get the flow of oil, for example, the flow of oil is just simply the area of that sector. Here is an equation for the flow of the oil. The area of that sector, let's say sector number 3, times the holdup within that sector of oil, times the velocity of the fluid in that sector. And that will give us a Q in that particular sector. Now, if we sum up all of the sectors, that will give us all 8 sectors, that will give us the total Q flow rate at that point in the wellbore. We can do the same thing for gas, same thing for water. Excuse me. This is an illustration of how the data might be recorded. Up here, you see the velocity data. Notice there are 3 of them here, row 8, row 7, row 2, and row 1. And here's the spinner. This does not show row 3 and 6 because this is data from an earlier tool. Here we have the flow profile. Notice that the lower 2/3 of it is relatively constant. It doesn't change very much. All of the action is up at the top here because that's where the gas is. You could do a hand calculation if you want, but you can see here what the problem is going to be. Here are the holdups. There are green and blue stripes here. That would indicate the holdup of oil, holdup of water. These red things here show the slugs going by. And what we're looking at is a period of time from 50, 60, 70, 80 seconds. So we're looking at a 30-second period of time. So if you were to do a hand calculation, the likelihood of you're getting something which is reasonably close to average wouldn't be very good. You'd have to do a number of calculations in order to sum all of these and get an adequate average. In any case, this is what the Polaris system did. The Polaris system did a very good job, but it's since been updated. So let me show you some of the new services. Okay, here is a tool called the FloScan Imager. Schlumberger came up with this back in about 2005, I think. And what it shows is it shows an A-frame structure here. So that A-frame structure basically opens up downhole, and on that A-frame you find a series of spinners, 1, 2, 3, 4, and then there's a 5th spinner here in the tool housing. The other side of the A-frame structure it indicates here 4 optical, 4 electrical probes, but really it's 5 and 5. The optical probe is the probe that's used in the Ghost tool. The electrical probe is the probe that's used in the Deft tool. And what you have, these probes here on this arm measure what the fluids are present, so it gives you the holdup of the individual phases, oil, water, and gas. These give you the velocity through 1, 2, 3, 4, 5 sectors across the wellbore. So you're seeing the same sectoring that we had seen before. On this figure, what I have here is an array of 1, 2, 3, 4, 5 little circles. Each of those circles represents the position of one of the 5 spinners. And what we have here are the velocities as indicated by those spinners. Actually, this is a measurement of the revolutions per second, and then that could be converted to a velocity. Schlumberger has calibration curves for these spinners. So here we have 1, 2, 3, 4, 5 different velocities across the wellbore. So this is a very uniform stratified flow. Here we have downflow. Downflow, I might mention, is like water going down a rain gutter. The heavy phase runs down real fast, and there's basically nothing going on above that. And this shows again, the spinners. By the way, if you look carefully here, you'll see Mickey Mouse on top. Mickey Mouse has 2 ears. One ear is the ghost sensor, the other ear is the depth sensor. Mickey Mouse's eyes, ghost sensor, depth sensor. Mickey Mouse's bow tie, ghost sensor, depth sensor. Remember, I told you that the upper part of the wellbore is where all of the excitement is. Down here, things get to be fairly calm, and there are fewer sensors down here in the lower half of the wellbore. Here we have an upflow. I might mention that you see here the light phase moving up very quickly at the high side. Generally, if you have an upflow, that flow can be very violent and slugging. Here we have the classic fallback, 45-degree well. You see the gas phase going up here and oil phases going up, carrying a substantial amount of water with them. What we find on the low side is we find basically water mostly coming back on the low side of the pipe. So here's the fallback phenomenon. This shows it again. This is a computed process log that Schlumberger would have seen. What it highlights here is the RPS is shown here. This is the rotational speed of the spinner that we had looked at. Schlumberger uses H as his indication of fluid holdup. So this is the water holdup. You see in this case, the gas holdup is 0. Why? Because there's no gas present. It's basically a mixture of oil and water. And here we have the well deviation angle, 47 degrees. And this shows how we do the computation again. We have 1, 2, 3, 4, 5 sectors. We have a velocity in each sector. hold up how much oil, how much gas, how much oil, how much gas, how much water in each sector, so we can then come up with the individual phase productions in each of these 5 sectors, add those 5 sectors together, and that would give us the total flow rate. Hold on. What I'm showing is the next tool, and the most recent to have been developed. This is from Sondex. Sondex is now a GE company, and it's also associated with Baker Hughes. What you have here is a tool that is part of what Sondex refers to as the MAPS, M-A-P-S system. That MAPS system, if you look very carefully here, has a series of 6 individual centralizer arms. These centralizer arms are not strong. They don't hold the tool up. If I were to put it on the table, the tool mandrel would fall right down to the table. The tool housing would fall to the table. But if you look at it, the purpose of these is to support the sensor some distance away from the tool near the wellbore. If you look very carefully, you'll see there are 1, 2, 3, 4, 5, 6 spinner elements here. These spinner elements are painted black, or they're black plastic, but basically if you were to go to a grocery store and go to the pasta section, if you get a spiral pasta and break it into about a 1-inch section, what you have is a Sondex spinner. Not really, but you understand. It reminds me of pasta. So this is a spinner array tool, a SAT. The other tools that the Sondex has and General Electric now is they have a tool called a RAT, resistance array tool. So we have a spinner array tool here, resistance array tool, R-A-T on the tool string. The resistance array tool is very, very, very similar to the DEVT. It has a resistance probe on it and can discriminate water from hydrocarbons generally. And then lastly, there's a tool called a CAT, capacitance array tool. That capacitance array tool can discriminate, I think, all 3 phases, but it's a fairly large diameter tool, and it cannot, in general, discriminate very tiny bubbles and stuff. So the Sondex tool will have the CAT and the RAT. The CAT and the RAT each have 12 sensors. So if you were to look at the distribution or the positions of the sensors, what you have is this. The spinner array tool has 6 sensors at the perimeter. The RAT and the CAT will each have 12 sensors at the periphery right close to the wellbore. Now, by the time you rig up a tool with a SAT, a CAT, and a RAT, the tool's 15 feet long, or even longer than that. And so this is one problem, in that what you're reading at the SAT is not necessarily the same as the CAT. But notice you can break it up into a series of horizontal sectors, just as we have shown here. And these will generally be in some sector. I might mention that as you're logging, the cable will tend to unwind, and these sensors will typically spiral around the wellbore. So if some of these sensors get plugged up or are non-functional, you can still get very good data because the sensors are essentially rotating and going around the whole wellbore. The next generation of tools that you're going to see are going to have some other things. One of the things you're going to see is the placement of spinners here midway between the tool mandrel and the housing. The other thing you're going to see is you're probably going to see the same thing done with the various fluid identification sensors. You're going to see probably fewer of them, 6 the depth sensor, or 6 RATs, 6 CATs, or maybe 12 with sensors in the middle over here. And they're all going to be trying to put these on a single centralizer arm so that all of the sensors will be at about the same depth. In any case, that's the next generation of tool, and I'll talk to you about that again in 2 years, I guess, or 3 years. By the way, I think, Sondex has missed the boat here in one thing. They call the spinner array tool a SAT. SAT? SAT? What's a SAT? It doesn't reach out and grab you, They should have called it a flow meter array tool, so that when you call out a job, you call up and you say, hey guys, we want to run a fat rat. Hey guys, we want to run a fat cat. Oh yeah, we got fat cats. And it'd be a great for business. One other thing, and then I'm going to be finished. And that is, when you look at horizontal environments, you have typically an undulating well like this. The low spots accumulate water, the high spots accumulate gas. These water puddles and these gas puddles are in general very difficult to get out. The flow in general will not be high enough to displace these necessarily. So as a result, what's going to happen is they affect the flow available, or the area available to flow. So this is why the calculation here is further complicated. Anyway, I hope that you've enjoyed this, and I hope that it's been or will be helpful to you, and I hope to see you at one of our SCA courses. Thank you.
Thanks, Jim. Thanks, Jim. Now we have time for some questions from our audience. So the first question has already come in. How much is production logging applied in the fields these days?
How much?
How frequently do production logs get run?
Well, I'll tell you what, compared to 5 years ago, it's gone from like 60 to 0. Maybe I'm exaggerating, but maybe nobody runs production logs in this economic environment that we have. They're very, very few and far between right now. At least the PLT type logs like we've talked about. Okay,
so that really begs the next question. How often would you recommend that production logs be run in a typical environment?
Well, let's forget about the financial environment. Then you're looking at doing the reservoir properly. Probably every couple of years would be a good option to run spinner flow meters, fluid identification devices. It depends on how complex the reservoir is and how fast you expect it to start producing water, because you can see these things coming with production logs or pulse neutron logs. You can see it coming ahead of time, so you can get some gauge of when you're going to have to do something with the well. So probably every 2 or 3 years.
So what's the risk that this tool can get stuck in the hole?
Well, don't forget, this is cased hole. It's not open hole. So we have now, you can run these in open hole too. If it's in open hole, obviously the risk of getting stuck is a lot more, because you can get the cable sticking due to differential pressure. You can get the tools sticking due to differential pressure against the wellbore and so on. But in cased hole, I don't think the likelihood of getting stuck is very high, especially if you run a weight in the hole initially just to make sure it's clear. I don't think there's a problem with getting stuck. It's not a big deal.
So are these tools often used to determine contacts, oil water contacts, gas water contacts, that sort of thing?
Not the production logging tools. The production logging tools would basically see what's coming in at each perforation. Now, the pulse neutron tools would be used typically to find those water oil contacts or water gas contacts. So the pulse neutron would look out in the casing. It would tell you what fluids are out there. Then what you have to do is look at what's being produced and make sure the two correlate with each other. Because if they don't, that means that perhaps you have something coming in through a channel. For example,
Okay, what about when you've calculated the holdup, you've referred to the holdup several times, how do you determine what the cut is? The holdup is the fraction of the volume present, and you said the cut was the fraction of the fluid present, moving.
relative to the other phase. That slip velocity means that we'll have different, the cuts and the holdups will generally be very different. Now, if the flow rates are very high, the cut and the holdup gradually approach each other and they can become the same because the velocity is very, very, very high and the difference between the two is not much. So, but as a general proposition, it's due to the slip velocity, and we have charts that will give us a handle on what that slip velocity is for both gas and oil in water.
Okay, our next question is, can this tool be used in estimation of permeability, and how reliable is this estimation?
There's a paper out by some guys at Chevron in Kazakhstan, and they brought all this together. And what they were trying to do, let's see, it was Dave Ballinger and can't remember who the other guys are right now. But anyway, you cannot in general calculate the permeability, but you can check what the actual production is versus the expected production. And insofar as it doesn't appear to be proper, that may be an indication that either the permeability is incorrect or else the permeability is damaged. There's a damage zone. So if you tie in the open hole and the cased hole data, you can get a handle on what the permeability is or the credibility of your open hole permeability.
Okay. So we're nearing the end of our time today, so I'll ask our listeners to put in one more question if they have any more. And I want to remind everyone that you'll receive a link to the recording of today's webinar. We'll send you an evaluation form and a link to registration details for Dr. Simone's class on cased hole and production log evaluation that's offered in June in Houston. And of course, we can offer it in your location as well. We have a listener that asked if you could repeat the answer to the holdup versus the cut question because the audio was a bit difficult at that point. So the question was, if the holdup is the fraction of volumes present and cut is the fraction of fluid movement.
Imagine a wellbore. You can have flowing. The flow and the cut are different. For example, if you have a standing pipe and you have bubbles going up, the volume of water, if you were to flash freeze it, would be about, let's just say 80% water, 20% oil, okay? That would be a measure of the holdup, how much is present. It's a snapshot, it's not a dynamic thing. But if you looked at the flow, the bubbles would be propagating up through the water at about 30 feet per minute relative to the water. So you would have a lot more oil. You would have much more than 20% oil coming out. You might have 60% oil cut, 40% water cut. But the holdup would be 80% water and 20% oil. And the reason is that one phase is migrating up relative to the other. And
great.
So
thanks for repeating that.
You can look at holdup as an allocation of how much of that pipe cross-sectional area belongs to the oil, how much of it belongs to the water. So you can see the pipe as two separate pipelines.
Great. Thanks very much. So thanks to all our listeners for attending today's webinar. As we mentioned, you'll get a link to the recording of the webinar and registration details for Jim's class. And we'll see you later. Thanks. Bye.